Rodriguez, but I'll be your lecturer next week. And here's what I thought I might try to do. Rather than walk in with a prepared lecture, we'll see how this works. But I don't intend to walk in with much of a prepared lecture. Instead, I'm handing out this paper, this essay. It's not paper. This week, as you get a chance, or over the weekend, read it. My email address is up at the top. Send me any questions or issues or comments you have. And then what I'll try to do in the lecture is comment on it, and then we'll have a kind of free-for-all. And you can bring tomatoes, and we'll see what happens from there. But I thought I would give you some preparation, and it would put me on the spot, and I'd have to do most of the work. Thank you.
Okay, so now we can come and start the official lecture this week. It's a great pleasure to have Roderick Kamoka, who's going to talk to us about Bohmian mechanics. So get your question ready, and we will have them answered in the next hour or on Thursday. Thanks, Roderick.
Thank you very much, Raymond, and also to Joseph, who I believe will be coming in a couple of minutes, for the invitation to speak here, to give 2 lectures in this course, 2 lectures about Bohmian mechanics. Let me start to get you into the mood with a quotation from Richard Feynman about the foundational problems of quantum mechanics. This is maybe a quotation that you've seen several times. Nevertheless, let me read it to you. Does this mean that my observations become real only when I observe an observer observing something as it happens? This is a horrible viewpoint. Do you seriously entertain the thought that without observer, there is no reality? Which observer? Any observer? Is a fly an observer? Is a star an observer? Was there no reality before 10 to the 9 BC, before life began? Or are you the observer? Then there's no reality to the world after you're dead. I know a number of otherwise respectable physicists who have bought life insurance. By what philosophy will the universe without man be understood? Now, Bohmian mechanics is a proposed theory of quantum mechanics that addresses these concerns. There are several names for Bohmian mechanics. It's also known as pilot wave theory. That's the name that de Broglie coined for it. Bohm himself called it, not Bohmian mechanics, of course, he called it ontological interpretation of quantum mechanics. John Bell called it de Broglie-Bohm theory. That has become a widespread name. There are other names as well. All of these names mean the same thing. And the name that I like best is Bohmian mechanics. Let me start by saying what this theory says, the definition. Well, maybe I should say, first of all, please don't hesitate to ask questions, to interrupt me in the middle of anything. If there's something that you want to ask, or that you feel needs clarification or discussion. So here's what I'm writing down is a version of Bohmian mechanics that's suitable for n-spinless particles in non-relativistic spacetime. I will say on Thursday something about how to do this in a relativistic spacetime, how to do this with spin, how to do this with a variable number of particles. Now, here's just the simplest version that I'm presenting. The main idea, or the main claim of Bohmian mechanics is that electrons and other elementary particles are particles in the literal sense, in the sense that they have precise positions at every time t. So they are particles in the same sense as in classical mechanics. That is, a particle is a very small object, possibly diameter 0. So the way it's modeled mathematically is just by one point in space. And this point kind of changes with time. It's moving around. So at every time t, it has a position, q of t. So this boldface q means a 3-dimensional vector. k is the index that numbers the particles from 1 to n. And now these particles are moving around in space. Let me write Q without boldface for the configuration, that is the positions of all particles. And then we have some equation for how these positions change with time. Okay, so it's an equation that determines the velocities of all the particles once we know all their positions. And this equation involves psi function, a wave function. The wave function, yeah, you're familiar with wave functions from quantum mechanics. So this is a time-dependent function on the configuration space. This is the appropriate configuration space for n. Yes,
I just had a question about the notation. On the first bubble, the equation, is it the right-hand side a function of Q of t? Or do you mean, are those brackets like for multiplying?
No, it's a function of Q of t. Right. That's because psi is a function of configuration space. The gradient, or any particular derivative of psi, is a function of configuration space. You evaluate both of these at the actual configuration Q of t. Okay, so the wave function is the same kind of wave function as in quantum mechanics. It evolves according to the Schrödinger equation. And the third, the third axiom of Bohmian mechanics is about probabilities and says there's a probability distribution. The probability distribution of the configuration at time t is the psi squared distribution, with psi the wave function at time t. This kind of theory has been discovered kind of by several people. Bohm was the person who first clearly understood that it actually deals with all of quantum mechanics, but these equations were first considered by Louis de Broglie in 1926, and similar ideas were proposed by John Slater even earlier. Now let me, yes?
So are these equations invariant under Galilean transformation?
Yes, they are.
So here you are given big, so here you are given dq dt in terms of psi. So, I mean, there's no force. There's the first derivative of q is given in terms of something.
Right. Yeah. Let me come back to this in a minute. Let me talk some more about the structure of these equations. Okay. Just another copy of the equation of the bubble that I had before. Now, let me call this expression here. So now I want to discuss this equation. Let me introduce this abbreviation for this expression. So it's kind of the v vector, the velocity. It depends on the entire configuration, and it depends on the wave function. Now, putting all these v vectors together, we get a vector on configuration space. So that is now a 3n-dimensional vector field. And these equations can then be combined to this 3n-dimensional equation, saying the rate at which the configuration changes is given by this vector field. Now, this means it's a first-order ODE, ordinary differential equation. So once you know what the wave function is, you get this time-dependent vector field on configuration space. And the configuration Q of t as a function of time is an integral curve of this time-dependent vector field. This means, in particular, that the theory is deterministic. Let me make explicit what that means. So for any initial time, t0, suppose we're given what we can now regard as initial data, a wave function t0 and a configuration t0. Then the Schrödinger equation determines the wave function for every time t. And Bohm's equation of motion, that is this equation here, equivalently this one here, then determines the configuration at every time t, because it's a first-order differential equation. Okay, so first order means you You don't have to specify initial positions and velocities as we would in second order, but just initial positions. Okay. Because of this determinism, it is appropriate for this theory to regard as a description of the state of the system at time t, the pair consisting of the configuration of the positions of all particles at time t and the wave function at time t. That's because with these two objects given, with this information given, we can compute the corresponding pair for any other time t. Now, coming back to the Galilean invariance, so the entire theory here is of first order. We're talking about velocities, not accelerations. And the way it becomes Galilean invariant, well, Galilean invariance contains several things: invariance under translations, rotations, and Galilean boosts. The invariance under translations and rotations is pretty obvious from these equations. If you translate, under the translation of space, you will change all of these of the positions by adding the same constant. So you will also translate the wave function in the same way, so that this equation is actually not affected. The same by rotating. You see, you're looking here at the gradient. If you rotate the wave function in a certain way, and you rotate the configuration in the same way, then also these gradients will rotate in the same way as they should. So that means you obtain the entire rotated trajectories from rotated initial data. Now, for Galilean boosts, what happens is that you have to, that is, as in standard quantum mechanics, you have to change the wave function by a certain phase factor that depends on the boost. And if you do that, then the new wave function, the boosted wave function, is again a solution of the Schrödinger equation. And then if you do the computation, you find out, oh, you get an additional sum in this from this formula. Okay. Here's an example where these trajectories are computed. This is for the two-slit experiment. So what's happening here? This is the first slit. This is the second slit. So the wave comes from the left, and most of the wave gets actually absorbed at these parts of these screens, except at the holes. So part of the wave function passes through the left hole, the upper hole, part through the lower hole, and then propagates towards the right. And the same happens with these trajectories. So what you see here, these curves here are alternative possible trajectories of the Bohmian particle. For particles arriving here from the left, many of these trajectories just end here because the particle gets absorbed. Those who make it through one of the two holes, they follow one of these trajectories depicted here. What you see nicely in this picture is a wave-particle duality in the literal sense. By this I mean there's a wave and there's a particle. So it's not a kind of mysterious sort of wave-particle duality, where somehow the same thing is supposed to be a wave and a particle, or can be looked at as a wave or a particle. You simply have two things, the wave and the particle. They're both there. And the motion of the particle depends on the wave. Okay, I will come back to this picture several times. Some more comments about the probability axiom. It is a consequence of determinism that once we've chosen the initial configuration and the initial wave function, everything else is fixed. So if the initial configuration, Q of t0, is random with a particular probability density, then it is fixed by the mathematics, by the equations. probability distribution of qt at any other time t will be. Namely, it's determined by this continuity equation or probability transport equation. So that means that this term here in brackets, that's just the probability current that you obtain from this motion, this law of motion with these probabilities. Now here's the basic fact. It's called the equivariance theorem. If the initial probability distribution is psi squared, with psi the initial wave function, then the probability distribution at any other time t is again psi squared with psi the wave function at time t. So this is a bit similar to invariant measures that you encounter in statistical mechanics, where phase-space volume is an invariant measure. Here it's called equivariant, which means that that both the probability density and the wave function psi evolve in a way that is compatible with each other. That is, you obtain the same probability distribution whether you evolve the wave function from time t0 to time t and then square it, or if you start with a probability distribution at time t0 and then just transport it along the motion of these alternative trajectories. The proof of this equivariance theorem is a simple calculation that is, well, it's a consequence of this equation here, which is the same equation as the one above, just with rho t replaced by psi t squared. So the proof is essentially a proof of this equation, and then the conclusion that psi t squared satisfies the transport equation required of rho t. So then you obtain as a conclusion, if you start with psi squared, you end up with psi squared. And this equation, that's just a consequence of the Schrödinger equation, which follows just by some algebra. And this equation is actually known as the continuity equation associated with the Schrödinger equation. You should notice that psi squared times the velocity gives you an expression that is known in kind of standard quantum mechanics as the probability current associated with the wave function. Okay, so I guess most of you have seen this kind of calculation before that checks this continuity equation from the Schrödinger equation. Now let me come back to this picture of the Bohmian trajectories in the two-slit experiment, and let's see where we can see equivariance in this picture. What we have here at the slit, just the psi squared distribution is sort of uniform here and uniform here, and the selection of trajectories that you see here are sort of uniformly sampled from the psi squared distribution. So what you see here is indeed a psi squared sample. Well, they're not actually sampled randomly, but to make the picture look nicer, they're sampled at equal distances. And then what you obtain at the end is a psi squared distribution of the arrival points of the particle on the screen. Here's a formulation of John Bell that expresses what I just said in words nicer than I could say it. De Broglie showed in detail, that refers to the fact that these equations were first considered by de Broglie. De Broglie showed in detail how the motion of a particle passing through just one of two holes in the screen could be influenced by waves propagating through both holes, and so influenced that the particle does not go where the waves cancel out, but is attracted to where they cooperate. So at points like this, where psi is 0, and therefore the psi squared is 0, none of the trajectories arrive. whereas in regions where psi squared is large, many trajectories arise. Here's,
Sorry, can you express the equation of motion in the form of second law, second Newton law, or?
okay.
Force.
It is a first-order differential equation,
Yeah.
and you can always transform that into a second-order equation by taking the time derivative. So the equation that we have is first order. Now we could take the time derivative of that. Then we have the acceleration on the left-hand side. And here we get some expression evaluated at this point of configuration space. And then we could call this expression here the force. And actually, Bohm called it the quantum force. However, this is not necessarily a good way of looking at the situation, because really the actual equation of motion is first order, and that is a fact that gets lost when you write down this here. Secondly, the expression that you get for the quantum force is kind of complicated and kind of arbitrary compared to the relatively simple expression that you get for the velocity here. And there's not necessarily any particular advantage with writing it in that way. However, you can always do that. It is advantageous to write it in this way if you want to look at the classical limit, if you want to look at the question under which conditions do the Bohmian trajectories become equal to or close to Newtonian trajectories.
So, so before you can solve this equation for Q, you need to get psi, right?
Right.
Psi comes from the Schrodinger equation, which already has all the information about forces, et cetera, et cetera.
Right.
So you don't, it seems like you don't really, all that information about what's causing the dynamics is already packaged in psi. It's equation of motion thereof. So that's already in there. So it doesn't seem really necessary to bring a force picture to the equation of motion at this level, because all that information is already packaged in there.
Right. For example, if you look at the trajectory of the moon in Bohmian mechanics, then the result that you obtain is that that the right-hand side of this equation will just be the Newtonian gravitational force, and other terms will be negligible compared to that. So what you obtain in such a situation is that the Bohmian trajectory becomes a Newtonian trajectory, and that's essentially because the wave function travels along more or less a Newtonian trajectory.
Excuse me.
Yeah.
What forbids you to have Q and EQ, ET as independent parameter that you can, is there anything that forbids you that you can prepare states or particles in some specific Q and specific EQ?
That would be a different theory then. It would no longer be Bohmian mechanics, because in Bohmian mechanics, you would always have this equation between the position and the velocity. Okay, so for a particular position, given the wave function, there's only one velocity possible. Now, if you could consider the possibility of writing down this equation instead, and allow the velocity to be determined, to be chosen as an initial datum, and later to be determined by this equation as in classical mechanics, then you get different trajectories, you get a different theory, and the ultimate outcome will be that the theory that you get in this way does not reproduce what we observe from quantum mechanics. Okay, for example, it does not reproduce the interference pattern in the two-slit experiment.
So I'm trying to understand, to see whether can you understand this theory as something in the as some classical dynamic theory, and then when you have given some specific potential, and then I mean, can you understand that in that framework, or?
So you can write it in this way, okay, and then you get a term that depends on the wave function. You get such a term on the right-hand side, but this is not necessarily a good way of thinking about the theory, because then this term is somewhat complicated and looks rather mysterious. Indeed, it would be mysterious if we had the idea that it's really a classical world and there's just kind of a new kind of force that was hitherto not discovered, and now we've discovered a new force. Then this force would look kind of mysterious, and things look much more simple and natural if you think of it as an equation of motion that's first order. So you go away from the general scheme of Newtonian mechanics. You say, now this is a non-Newtonian, a new kind of mechanics. That's Bohmian mechanics. Okay? Here's another way of writing Bohm's equation of motion. That's a way that's often useful. So I'd like to make you aware of that. Suppose, consider the polar representation of a complex number, modulus and phase. So the phase, that's given by the s function. S is a real function. And for it is convenient to extract a constant h bar out of the s function. And r, that's just the absolute value of psi. So these are now real valued functions. Of course, they contain the same information as the complex wave function. And rewriting the equation of motion in terms of r and s, we obtain it's up to a factor, up to a constant. It's just the gradient of s. The Schrödinger equation itself, when you write it in terms of r and s, doesn't become simpler. It becomes a bit more complicated. One of the equations is the continuity equation, and the other is an equation for the time derivative of s that has some similarity with the classical Hamilton-Jacobi equation. There is a problem, though, with writing psi in this way in terms of modulus and phase. The problem has to do with the fact that the phase is not uniquely defined by the complex number. It's only defined up to 2 pi. So you could, at any point, add an integer multiple of 2 pi over h bar, 2 pi times h bar to s. And this has some unpleasant consequences. For example, when you go around a node, then actually the s function can change by an integer multiple of 2 pi h bar. So the s function cannot be written down as a continuous function of q, whereas psi is a continuous function of q. So there are some subtleties, some unpleasant consequences of writing in that way. So it's so that's the reason why I usually write everything directly in terms of psi. But it is sometimes useful to write the velocity vector field as the gradient, or 1 over mass times the gradient of the s function. Now let me quickly go over some ways of guessing Bohm's equation of motion. How would you arrive at this equation? Why would you think that that is a good equation? There are several quantum mechanics, you wouldn't say that an electron has a trajectory. You see, there's no, what this statement here said, the central fact, is there's no experiment that comes out one way if quantum mechanics is right, comes out another way if Bohmian mechanics is right.
That's true, but
Okay,
I'm saying
so-
for any theory, even for an, I don't know, for other theories like not just quantum mechanics, if you for any probabilistic theory, you can find very, very, very weird theory that gives you the same prediction, but it's not physics. I mean, I don't understand what's the.
Okay, let's see. So,
Sorry, we only have 10 minutes left for the lecture. Do you want to take this up after class?
okay, so the picture here is that some people think that something like this is needed to turn quantum mechanics into a good theory. So you disagree with that, so you have a different picture of what a satisfactory theory of quantum mechanics should be like. Okay, so now I would say what you should do is get some understanding of what people like myself think and why they think that. Okay, and well, you have your view and I have mine. Okay. Concerning the empirical predictions of quantum mechanics. So let me start again with a few simple observations about the two-slit experiment. So the particles, so for the two-slit experiment, it's sort of obvious why Bohmian mechanics makes the same predictions as standard quantum mechanics, because the particles do arrive at the screen with random positions with distribution psi squared. Here's some more observations. If one hole is closed, then the wave function behind the holes, behind the one hole, will be a very different one. And all the Bohmian trajectories will look differently. And they will have a different distribution over here at the screen, a different interference pattern. Okay? So also the fact that if you close one hole, then you get a different interference pattern with no fringes or different kind of fringes. That also comes out from Bohmian mechanics the right way. That's essentially because the wave passes through both holes, even though the particle passes only through one. Then if you ask the question, through which slit did the particle actually pass, that is easy to find out. You see, if the particle passes through the lower slit, then it will arrive at the lower half of the screen. And if it passes through the upper slit, it will arrive in the upper half of the screen. And that's basically because the trajectories can't cross. And that's basically because it's a first-order differential equation. Now, that seems, again, like it's in conflict with one of the things that you know about quantum mechanics. Namely, it's not possible when you have an interference pattern to know which slit the particle passed through. Now, how does that work out in Bohmian mechanics? The answer is, as we've just seen, it's easy to know which slit the particle passed through. But it is still true that if you put a detector near one of the slits, then actually the interference pattern will disappear. Why is that? That's also something that often sort of people think, well, couldn't I just, if the particle actually travels either through the upper or the lower slit, couldn't I somehow detect its electrostatic field or its gravitational field, and then detect the particle without disturbing the interference pattern? And here's why that doesn't work. It has something to do with the fact that your detection mechanism consists of Bohmian particles too, and there's a common wave function for all the Bohmian particles. So now let's look at a wave function. That's a wave function of both the particle that's passing through the double slit and the detector. So I've drawn only one component of the particle position and only one component of the detector configuration. Now, in these slides, These slides I had actually prepared for a case, not for the double slit experiment, but for a case where I started with a beam splitter. So beam splitter. So this is kind of the kind of wave function that we start with in the double slit arrangement. So for the particle that's in the double slit apparatus, we have a superposition of being here and being there. Sort of here's one slit, here's the other slit. Whereas in the detector variable, it's just in a certain region that corresponds to the detector not having detected anything. That's the ready state of the detector. Now, during the interaction between the detector and the particle, that will actually move one of the wave packets here to a different region of configuration space in such a way that now the particle coordinate here or here becomes correlated with some detector coordinates here or here. Now, starting from this situation, it becomes obvious why that will cost you the interference, because do I have an eraser here? And maybe I draw it on the other side. Now that you have this situation here, behind the double slit, these two wave packets will spread in the right direction, so this will become wider and wider. That's what the wave packet does after passing through the slit, and similar this one. And since they don't overlap in configuration space, there's no interference pattern. If you look at the probability distribution associated with just the particle coordinate, it's psi squared and then the detector variables integrated out. So what you get here is just the sum of of the squares of two wave packets, and there's no interference term. OK, so that's the reason why the interference pattern disappears when you put a detector in one of the slits. Yes, please. Pardon, give us what?
Luther's rule without having to postulate it? Like the collapse of the wave function, in other words.
Yeah.
It gives it to us without having to postulate that being like an additional axiom to our theory.
Yes, absolutely. Absolutely. I will come to that, well, maybe not today, but on Thursday. It's one of the later slides. Yes, that's exactly right. Another historical comment. So Richard Feynman, in the Feynman lectures, has a beautiful discussion of the double slit experiment. And there he claims that it's impossible to explain the double slit experiment. Here again, there's a situation where Feynman was just plainly wrong about this. So that's what we see now from having understood something about how the double slit experiment works in Bohmian mechanics. Here's, in John Bell's words, the broadest explanation seems to me so natural and simple to resolve the wave-particle dilemma in such a clear and ordinary way that it is a great mystery to me that it was so generally ignored. Now, after the double slit experiment, let's look at more general quantum measurements. Okay, so here are the kind of the quantum mechanical rules for a quantum measurement. So between the measurements, while the system is closed, its wave function evolves according to the Schrödinger equation, whereas at a measurement of some observable with this operator, self-adjoint operator, these are the projections to the eigenspaces, and alpha are the eigenvalues. Then here are the rules. This is the probability. It's the size of the contribution to the wave function from that subspace. And afterwards, finding a particular outcome alpha, we collapse the wave function in this way. So this means immediately after time t. OK, the same thing we get from Bohmian mechanics as just a consequence of the basic equations. Here's how that plays out. So we look at the wave function of system plus measurement apparatus, keeping in mind that the measurement apparatus in a Bohmian world consists of Bohmian particles as well. Now, the experiment starts at time t1. At that time, we assume that the wave function is of this product form with phi, the ready state of the apparatus. This assumption means that the object and the apparatus are independent of each other, and this is the only case in which we can talk about making an experiment on a system with wave function psi. So again, now let psi alpha be the eigenfunctions, say an orthonormal set of eigenfunctions of this operator, alpha the corresponding eigenvalues, and I will often have to denote the unitary time evolution corresponding to the Schrödinger equation from time t1 to t2, and I just write an arrow for that. Now, suppose we start with an eigenfunction. Then the kind of experiment we want to consider is one in which, with probability 1, we get the outcome alpha. OK, so that is what is expressed by this line here. If we start with the system being in an eigenstate and the apparatus being in the ready state, then what we end up is the same state of the system and some state of the apparatus in which the apparatus displays the value alpha as the outcome of the experiment. This, of course, is a kind of idealized setting. So let me just first discuss this idealized setting. Then it follows from the linearity of the Schrödinger equation that for a general initial state of the wave function, a superposition of different eigenvectors, we obtain this superposition of states of the composite system, different states, in which the apparatus actually displays different outcomes. OK, so this is just the analysis of what the Schrödinger equation does in a measurement situation. So here I've summarized the same thing. I've kept the main equations in this box. And now let's look at what the Bohmian particles do in this situation. Keep in mind that the pointer of the apparatus consists of Bohmian particles too, and thus points in some direction. Let's just assume for simplicity that it's a needle that cannot point either here or there or there. So the configuration of system and apparatus together at time t2, that is where we can read off where the actual needle consisting of Bohmian particles points. And this has probability distribution given by the appropriate psi squared. And in this case, the psi squared is a sum of the squares of the individual contributions. I did not forget the cross terms. In this case, the cross terms vanish because these functions phi alpha have disjoint supports in configuration space, or approximately disjoint supports. That corresponds to the following. If I want to consider wave functions for the apparatus corresponding to the pointer pointing here or pointing there, then this wave function that corresponds to the pointer pointing here should be near 0 on configurations in which the pointer is actually pointing there. That's why they have disjoint supports in configuration space. Keep in mind that these are functions of many, many variables, like 10 to the 20 variables. Okay. They have disjoint supports in configuration space. That's why the cross terms don't appear here. And that's why the probability of the pointer pointing in a particular direction, say the one corresponding to alpha 0, is obtained by integrating the probability density for the configuration over that region that corresponds to the pointer pointing in that direction. And that gives us, since these functions are normalized, just the corresponding coefficient squared, which is exactly the prediction of quantum mechanics. So this is in agreement with the measurement rule of quantum mechanics. And this is a derivation for certain idealized cases of the measurement postulate of quantum mechanics from Bohmian mechanics. The time is up. I think I stop here. I will continue at this point on Friday. Thank you very much for your attention.